It's great to announce our next speaker, Pierre Bieliavsky from the University of Louvain, who will talk about construction by Dorothea, Bahns and René Schultz.
Thank you very much. Hello to everybody. First, I have to say thank you very much to the organizers for this fantastic event, the first one since such a long time. And I'm very happy to see all of you, my friends, my colleagues. It's really great. Okay, so this will be some kind of user-friendly talk. So in the sense that there will be several colors used during the talk. So you will have first the black color, like this for, usual, as usual, regular information. And then you will have the blue color, which will be used for things that I would like to attract your attention. Okay, specific thing. And then there will be the brown color, which will be used for things that are totally irrelevant to the understanding of this talk. Okay, and then at last there will be the green color, which will be used for wrong statements, which I apologize. Okay, so let me tell you about these things. So let me tell you about my motivations. So I will talk about a construction. Basically, what I want to do is an advertisement of a construction by Dorothea and René Schultz, and also to report a small result I have in this context. So the motivation I have, I know that Dorothea and René, they have a motivation in quantum field theory for sure, but I don't have this motivation basically because I don't know quantum field theory. I'm just learning it at the moment. But I have motivation in star product theory and analysis in more specifically harmonic analysis on the Lie groups and homogeneous spaces. So there was an important question as soon as star product theory had been on the market, let's say at the end of the 70s, really, which was the question concerning the domain of a star product. So when you have a star, I'm talking, of course, of non-formal star products. So what is the domain of a star product? Well, it's not clear. It's a vague notion, which I've seen basically in papers by Fronsdal and Flatteau. But let's say the idea is that you want to be able to define a space of functions or distribution on a manifold on which your convergent star product is well defined. So there were many papers concerning this question. Can you hear me? Because the sound changed a little bit. It's okay. Oh, okay, yeah, okay. And of course, an important work, pioneering work, is the work by Maillard on the Weyl star products. Basically, we want to know what are the larger space of quantizable observables. That's the idea. Well, okay, I am interested in two type of basically in one type of star product. So the star products that are defined on homogeneous spaces and then that I ask to be required to be invariants under the group that acts. So first of all, for example, you have the star products on R2n that are translation invariants. For example, the Weyl star product, we'll see that, and also the standard ordered star product coming from the Kohn Nirenberg quantization. So that is certainly two star products that I will talk about. And then more generally, I'm interested in invariant star products on homogeneous spaces. So there was one that I like. Probably that's the good paper I have written in my career, which is well, the one I prefer. I'd say. I don't know if it's good, but it was a construction that I made for symmetric spaces, basically obtaining integral formulas, oscillatory integral formulas for convergent star products on symmetric spaces. And my aim there was to see it, right? Was to establish the strong relation between the analysis, the functional analysis, which is attached to these oscillatory integral formulas, and the geometry of the symmetric spaces you work on, right? So that was motivated basically by work of Alan Weinstein in the 90s. So that is one star product I like. Another star product I really like is the star product given by Weyl and Beiser on the hyperbolic disk. That's also a star product I would be very interested in. And also generalization of the star products and other things by Philip. So okay, that's the type of things I very much like. And then the story is that what happens when you have such a star product, which is invariant on a group or a Lie group or some homogeneous space, well, you get two things basically. You get two things that you could be interested in. You get first you get the notion of Drinfeld twist. So it's a kind of tool that can be used to deform the category of module algebras your group acts on. So basically, you take a Lie group, okay, and let's say formally at first, you look at the universal enveloping algebra of this Lie group, okay, and this is a bialgebra, okay, so you can look at the category of module algebras for this bialgebra, right? And the notion of twist is actually it's a gadget that was designed by Drinfeld in the 80s. It's a gadget that can be used for the following: as soon as you have a module algebra for your bialgebra, then you can use the twist to associative algebras. I'm talking about associative algebras. Then you can use the twist to deform this module algebra into an associative algebra. And therefore, you get a deformation of all the objects in the category of module algebras for your bialgebra. Well, for example, here, the universal enveloping algebra. Okay. But then you can ask yourself, okay, do I still have an action of the bialgebra I was starting with? Do I still have an action of this bialgebra on the deformed categories? Right. What are the symmetries of these deformed objects that I get? And the nice thing, the nice news is that actually you don't. You don't have such a thing. But you still have a notion of symmetry, and that is the quantum group. So the twist again enables you to build a new kind of object, which are quantum groups, and which can be seen as symmetries of the deformed categories of module algebras for a given bialgebra where you have a twist on. That's the thing. Of course, once as soon as you work in the formal or algebraic framework, all of this is very well known, let's say. But of course, when you start to think about topological algebras and topological quantum groups, then things will become much harder. And there are several constructions and several directions in analysis and in also in operator algebra theory, which have been developed concerning these objects, so Drinfeld twist convergence, Drinfeld twist, and quantum groups. So the one that I like are called locally compact quantum groups. So regarding the twist, okay. Regarding the twist, you have the first non-formal twist designed by Weyl based on the Weyl quantization, okay, for deforming the category of modular algebras on the abelian group RD. So that was a very nice book that he wrote about that in the 90s. What? The claim? Ah. Let me remind me if there is I think there is a mistake in the book. Yeah. No, that's a joke. I don't, that's another, that's a meta joke if you want. So let's use the purple thing here. Okay. And so there is this notion of star product that I told you about here. And these star products, the geometrical star product, can actually be used to define, well, that's a whole story, that can be used to define Drinfeld twist, but for non-actions of non-abelian Lie groups, and specifically Lie groups that carry an invariant, left invariant Kähler structure. So that was an answer to Weyl work, which we did with my friend and collaborator Victor Guéral. Okay, we wrote also a small book about that. And then you have a very nice work by Gandalf, Leichner, and Stefan, which is about application of the twist. So I'm talking about the Weyl, right? The Weyl twist Weyl. Application of the twist in the context of locally convex associative algebras, rather than C star here or Fréchet algebras that were considered by Weyl. And the thing is that the whole business depends on something, on some very important property, very important category, which is the smooth category. So everything is done in the smooth category. So you start with a C star algebra, a Banach algebra, something like this, of course. But then to run the machinery, you really need smoothness of the vector you look at smooth vectors of the action in the algebra. That's really, really, really important. Okay. And basically you use some kind of oscillatory integration by part form techniques. So smoothness is important. And then you have a completely different framework, which is the framework of C star algebras or von Neumann algebras, where you define the notion of symmetry, what should be the notion of symmetry of these deformed categories of modular algebras. But what happens, and this was put on the market by Bahns and R, and then amazingly developed by Kenny de Kommer. And then we have a small work, well, a work with Victor Nejvejev and Sergei Nejvejev and Lars Tusset on that. But the thing is, what I want to say is, I will talk about this work later. But what I want to say is that everything is done in the C star framework and not at all in the smooth context. And actually, in this theory at the moment, there are not so many examples. You have examples that were designed by Bahns and Skandalis in terms of this would be probably interesting for people who are doing Poisson geometry in terms of what they call match pairs. These are you know, some kind of groups, let's say groups which admit maybe a measurable decomposition into two parts, okay, two blocks, which are subgroup, and you have a addressing action of one onto another, right? So this is the type of things you have for examples there, and then we have developed another class of example. I hope to be able to talk about there. But these examples are based on the Kohn-Nirenberg quantization, while the twist and the smooth category are based on the Weyl ordered quantizations. And the thing is, and that's a question which was asked by Weyl at the beginning, of course, can you use Kohn-Nirenberg quantization, which is the most natural one, actually, if you think about it? Can you use Kohn-Nirenberg quantization to produce twists? And we don't know the answer. So there is really a dichotomy between these twists we have at our disposition and their category, their symmetries. Okay, so apparently these notions are pretty much competing, and I would like to understand a little bit these things. And I think Dorothea's idea, which is to start talking about real-fold deformations, but in the context of micro-local analysis, it's a good idea, and I believe that it could help in understanding this apparent paradox. Okay, so that are my motivations. I hope I will have time to talk about something. So let's start with the Moyal or the Weyl product. So you start with a finite dimensional symplectic vector space. I can't use green, but let me take blue. And you have the space of Schwartz function on this space. Basically, it's R2n. So you have the space of Schwartz function, which is something already you can make a remark there. The Schwartz functions, they are defined in terms of a norm on V, because you need polynomial, right? But there is no norm on V as soon as V is only symplectic. So there is a choice here of a complex structure. And that's something I hope to be able to talk about. So there is already one point there. But anyway, you have this integral formula here that defines an operator. Okay, so here you see the notations. So I take my point x bar in the square of V. Okay, with two components x1 and x2, and I have this phase here in the twist, and this phase is of course simply the symplectic structure applied to evaluate it on the points. And here I have this thing there, which denotes simply the translations, simply the translations, right? So you have in V square, you have this. Okay, that's just a notation for that. And so you act with this translation, you act on a Schwartz function on V star, on V square, and then you form this oscillatory integral. Okay, and what you get actually is a map. It's actually an isomorphism of automorphism of Fréchet space. You get a map from the Schwartz function on V square to itself. And the thing everybody knows here, of course, is that if you contract this map, if you follow this map, compose this map with the multiplication, pointwise multiplication of functions in the Schwartz space, then you get an associative product, and this is the Weyl product. And so basically the work of Dorothea and René is a way to define extension of this Schwartz algebra in terms of spaces of distributions, temporal distributions. Okay, so let me now describe their results. Hopefully, I have to introduce, unfortunately, a little bit of analysis here. So I start with my vector space V, right? And I have the space of symbols of order M, okay, where M is a real number, which is defined as follows. These are functions that are smooth on the cotangent bundle of V, and which have the property that if you take the derivative, they are bounded by a polynomial of the point they depend on. Okay, so that is the space of let's say uniformly bounded. That is the space of symbols. And then the nice thing is that you have this Weyl quantization. So namely to a symbol, you can associate an operator that acts on the Schwartz space of V by a formula that you all know, okay, which is the Weyl quantization formula. Again, defined in terms of an oscillatory integral. And the observation is that if you take a symbol of order minus infinity, and if you take a distribution, temper distribution on V, of course, you can define by duality, you can define the action of the operator on the distribution. And what happens is that if your order is minus infinity, then the result you get is actually Schwartz. So minus infinity symbols are smoothing. And the notion of wavefront set that I want to talk about, of course, due to Hermann there, basically everything I will talk about is due to Hermann there, is not the classical notion of wavefront sets of distribution, but it's a notion that actually refine this observation. So to define the notion of wavefront sets, it's called the smooth wavefront set by Olbermann, and it's called the G wavefront set by other people working in signal processing, for example. So the definition is the following. First, I have to define what is the characteristic set of a symbol. So suppose I take a symbol, okay, take a symbol of order M, okay, so a function on T star V, and suppose that I take a direction in the cotangent bundle of V. Okay, suppose I take a direction. So the first X, the first component is a component in V, and the psi is a component in V star. When you identify T star V with V times V star. And so I will say that such a direction is not characteristic. Okay, is not characteristic for the symbol. If when I look at the symbol restricted to the direction, then it really grows as a polynomial of order n. Of course, it could grow with a lower degree. For example, you could take a minus infinity symbol, then it decreases very fast, right? But a direction is non-characteristic if in this direction the symbol really grows as a m-order polynomial. Okay, now the definition of wavefront set is the following: is that an element will be in the wavefront set of your tempered distribution U, as soon as if you have a symbol of order m that smoothes the distribution, then the direction you are talking about must be characteristic for the symbol. So in other words, if you have a nice smoothing by a symbol in a direction of your tempered distribution you are starting with, it means that in fact the symbol is not really a polynomial. It's something that decreases faster. So that's the idea. Okay. So that's the notion of wavefront sets. I still have to continue a little bit talking about Olbermann stuff. So we will consider linear maps between vector spaces. So suppose I consider this is just a notation. Suppose I consider a linear map between two vector spaces like V and W. Okay, and suppose that I consider a set E in the cotangent space, cotangent bundle of my target space W. Then I will consider two vector spaces. So the first one, I will call it the kernel of A star. Okay, so this is simply the slice. This is simply the slice in the cotangent bundle of W. The slice 0 times W star, where A star vanishes. And then you have also a notion of pullback of a set in the dual in the cotangent space of W, which is defined like this. Okay, so this set here is actually a set in T star V. Okay, which is defined very naturally. Okay, so this is the things that you will look at. And then the proposition due to Olbermann, which will be crucial for us, is the following: is that if you have a distribution on the target space, tempered distribution on the target space, which admits the property that its wavefront set does not intersect the kernel of the transpose map of A. Okay. Then you can give a sense, a meaning to the pullback of this distribution by A. And you can give this meaning as an element of the tempered distribution of your source V. And even more, you have an information about the wavefront set of this pullback distribution, which is that the wavefront set of this pullback distribution is actually contained, always contained, in the pullback of the wavefront set of the distribution that you were starting with on the target space. And now the definition of the underlying spaces of these algebras that Dorothea and René considered is the following. The definition, which is again due to Olbermann. And this is the following: when you consider, so these wavefront sets, I forgot to say, these are closed cones. And you consider the fixed closed cone in your cotangent bundle. Okay. And you look at all the distributions that have the property that the wavefront set is contained in this fixed cone. Okay. And that is the space denoted by Olbermann, which we will consider. And then there is a first trivial remark, which is that if you look at the map that goes from V to V times U, which is just the diagonal map, okay? And if you consider a closed cone, let me call it gamma bar, in the cotangent bundle of the target of the diagonal map. Okay, so there. Then you have an observation, which is that, okay, it comes immediately from the proposition, right? Which is that if the cone you were starting with does not intersect the kernel of the transpose map of the diagonal, of course, you understand that this will play a role in defining the product, okay, of such distributions. And if you consider that if you assume that your cone gamma bar has a certain property, so namely that it's inverse, that it's pulled back by the diagonal map, square is in gamma bar. So that's a condition you require, and which is wrong actually. This is a little bit more complicated, but I'm not going to talk about the details. Okay, so this is very wrong, right? Okay, then making this completely wrong assumptions, you have that actually this space becomes an associative algebra where M0 is the pointwise multiplication product, which of course in general doesn't make any sense for temporal distributions, right? But in this context, you have an associative algebra which is commutative. Okay, and so what will Dorothea and René do is that they will simply replace, well, simply, there is some work, but they will replace this commutative product by the Weyl product. Okay. Now let me talk about their theorem. So I will phrase the theorem not exactly in the way they would phrase it. They phrased it originally in their paper. We'll phrase it in a way that will allow me to prove another theorem concerning another star product. Okay, but it happens that it turns out that actually this context works for many star products, basically all of the translation-invariant star products. So what is the framework? Well, you have this map. Okay, you have this map that goes. So have your V. You have your V, which is a symplectic vector space. So in particular, you have an identification between V and V star, and this identification I will call it sharp. So the sharp is simply the symplectic form, right? The sharp is the map that goes from V to V, from V star to V. Okay, identification through the symplectic structure. And I have this map that I call sigma that goes from V star times V star to V times V. Okay, and which is the one which is defined here, whatever it is. And then I have an operator that can be defined through this map. Okay, which is the following. So you start again with this cotangent bundle of the square, and the point G bar. So I call it G bar. I'm writing the letter G that I already use, right? Because in fact you need to what is underlying this setup is that in fact this T star V or V square or W they should be interpreted as subsets of the Heisenberg group. Everything is actually controlled by the representation theory of the Heisenberg group. So this is why I call it G, and the map is simply this one, right? You have this G, okay, so which is X bar psi bar, and you add simply sigma psi bar, where I remind you the sigma psi bar is something that lives not in V star, but in fact in VV. Okay, so this is the map, and I call it B because at first I wanted to call it BS for Bahns Schultz, right? But then it was a little bit long, so I prefer to use the B eventually. So the lemma we have with Louis, the man who is there, my student, is the following: is that if you take a closed cone in the cotangent bundle of the square. And if you assume that this cone is actually stable by the map B, okay, the map B, then actually your twists, I'm not talking about the star product, I'm talking about the twists, okay, the co-cycle, the Weyl co-cycle I defined, is actually an automorphism of this space, which is not yet an algebra. Okay, sigma prime gamma bar v square is not yet an algebra, but this is some space of distribution which is stable under the Weyl twist. And now the theorem of Bahns and Schultz can be phrased as follows. It's not exactly their theorem. Not exactly. They work with a set of cones that is a little bit different from those that we consider with Louis. So I guess, but I'm not completely sure. But I think the phrasing that I have here is maybe a little bit stronger than theirs. So just a little bit, I think. But I'm not completely sure. Okay. So the hypotheses are, of course, the stability of gamma bar under this map B right here, and then the way that you can take their pointwise product, which is, as we see, this condition, okay, and the property that enables you to repeat the operation of taking products, which is actually this wrong condition here. Okay, and then under these three conditions, you have that this space is actually an associative algebra. I think this theorem is really great. I mean, I like very much this theorem. Okay, so the way they prove this theorem is they use essentially Olbermann theory, and basically they use a lemma due to Olbermann that establishes a compatibility between the wavefront sets and the Fourier transform. The idea is that they express the Moyal or the Weyl product in terms of Fourier transform of a twisted convolution product, and that is really an important thing for them. Okay, in our context, we do not do that, and that's the whole point, because this is very specific to Weyl product, that you can indeed express it as a intertwined product via the Fourier transform. Of course, for example, the Kohn-Nirenberg product cannot be expressed in these terms, and so at first the methods Dorothea and René use are not going to work as such, at least in the context of a more general translation-invariant star product. Okay, so that's it. That's the result by Dorothea and René. So I'm going to talk about something completely irrelevant to the understanding of this talk, but I would like just to advertise the fact that these algebras constructed by Dorothea and René are actually interesting. And so the precise statement is the following, and this is so you don't need to read all this thing, but the fact is, okay, now I am talking, I guess, to people who spent a lot of time a lot of their time integrating by parts. Okay. So the thing is, the thing is that okay, you can define on this Hermander spaces or distribution, you can define a topology, a locally convex topology, and which is defined in terms of the condition on the wavefront sets, of course. And you can also define commutative. We did it, right? Observe that you can extend the commutative product of functions on these distribution by slight assumptions on the cone, on the defining cone of your distribution space. And then you have refold machinery, right? You have an action of RD V on this space of distributions that respects the topology of Hermander, no problem. And you have refold machinery. And so I have to confess that to Dorothea, I never dare to tell her that, but no, okay, this is a good occasion if she's there. I have to confess that I believe that first, that their algebras were just refold deformations. And so I started to think about the machinery we developed with Geiral, and in the non-abelian case, or equivalently in the abelian case developed by Stefan and Gandalf, which is running the refold twist on locally convex algebras, and that doesn't work at all, because I'm not going to talk about the details, but the important condition, you have on this. Yeah, I have a virus on the thing. The important condition, which is used crucially to get the deformation of the locally convex algebra, you have this action of V on. Is violated. Definitely. I mean, it is not just that we weren't smart enough to prove it. It's simply violated. Okay. So the smart guy who proved that it is indeed violated is Heiner Olbermann, with who the paper is actually joined. Okay, so there are interesting algebras that are not refold deformations. Okay. So let me tell you a little bit about what we did. So you start with this symplectic vector space, but you do something non-canonical here. You actually fix a Lagrangian decomposition. Q and P. Okay. And then you have, in an analogous way as you have for the Weyl product, for the Weyl twist, okay, you have this operator that goes from the Schwartz functions on the square to itself, okay, which is defined in the same way, okay, as the Weyl twist, except that the kernel here, which was in the Weyl case, the phase given by the symplectic structure, that was the Weyl case, okay, is actually not the same. It is given by a distributional kernel, which is this one. Okay, you see delta function, delta distribution appearing there. And okay, the thing you prove, it takes essentially 5 minutes when you are when you had your coffee, you prove that it is indeed an automorphism of the Schwartz space of the square. And again, what everybody knows is that when you compose, you have the same result as in Weyl. When you compose the twist with the pointwise multiplication, you have an associative algebra structure on the Schwartz space of V. Okay, so that is the Nirenberg co-cycle, but you see this kernel, okay, which is there. Okay, So that is the star product I will be, at least one star product I will be interested in. And why specifically this one? Okay, I remind you, why this one? This one, of course, it's very natural one. Okay, it's the one which work for cotangent bundle, which Weyl doesn't do as soon as you don't have a global parallelism. Okay, so that's a very, very nice product. But above all, that is the star product for which referral machinery doesn't work, and that's exactly this one that I want to consider, and not only because I would like to solve a problem, okay, which is defining a deformation machinery for a non-oscillatory integral star product. It's not because I like to prove that or to solve this problem. This is because it turns out that with our work with Nejveev, Tussetz, and Geyral, we prove that the Kohn-Nirenberg 2 co-cycle Kohn-Nirenberg 2 co-cycle, we have the notion of locally compact quantum group. So we can associate to this object, we can associate locally compact quantum group. So in particular, if we can prove that this twist gives a universal deformation formula, then we have a link between the two things, right? That's why I am so interested in this star product. And so we have the same theorem basically as Dorothea and René, but of course now the proof is completely different. We have again a map B. Okay, we have again a map B as we had in the context of Bahns-Schultz, except that this map B is a little bit different. You have this map sigma. You remember we had before, that was given by basically the symplectic structure. Okay, here it's a little bit different. You have a decomposition of V in Lagrangians, right? So you have a decomposition of V star in Lagrangians, and this is this decomposition. It is denoted by these upper index 1 and 2. Okay, so this is the thing, and the map does this. Okay, that is the map. So it is different. It is different for sure. And then you can define the Bahns-Schultz operator the same way. Okay, that's the same formula here. Okay, again, you should interpret this formula in terms of a map between the Heisenberg group and itself. Okay, but here I'm just looking at the symplectic vector space part of the Heisenberg group. Okay, so you have this map analog to the Bahns-Schultz, except that the sigma is different. And then you have the same theorem. So first you have the same lemma. If you assume your closed cone in the cotangent bundle of the square to be stable under the Kohn-Nirenberg map B, then you have a twist. Then you have a twist on the Hermander space on the square associated to the cone. And the theorem now is the same as Dorothea's and René's, which is that under these conditions, same conditions, well, the space, the Hermander space, is stable under the Kohn-Nirenberg star product. So one small remark is that the cones that are involved, are of different type than the one Dorothea and René considers. So okay, so Somehow they are less constrained because if you look at this map sigma, okay, it's actually simpler in some sense. Okay, you have zeros that appear there, so the cones are less constrained. So you have larger sets of admissible tempered distribution algebras. Okay, so that is the theorem I wanted to show you. And now I just forgot what I want to tell you, but in the next slides, yeah, I'm not going to talk about the proof. So I'm just telling you that, okay, there is an important piece, which is a work by Rudino, which is a characterization of Hermander smooth wavefront sets in terms of basically Fourier transforms. Okay, so that is a very well-known result. Dorothea and René use very crucially. Okay, so that's something which is completely common to our proof. But then this Rudino result is actually combined with the orbit method of Kirillov to construct a unitary irreducible representation of your group, which is in this case the Heisenberg group. And so there is a hope, there is a hope that this type of method, because you see the orbit method appearing there, so there is a hope that this type of method would work for other type of symplectic groups. For example, the Lie group that carry left invariant Kähler structure. So precisely the one that we dealt with Victor Gerhal. Okay, so now just for the fun, because I like these formulas and that I have still half an hour. So I will talk about translation invariant two-code cycles. Okay, so I've looked in the physics. No, I've looked in the mathematics literature on Google, translation invariant star product. I typed it, and I didn't find a lot of things in the mathematic literature. Maybe I didn't look enough. I don't know. All of them. So Weyl is an example. Nirenberg is an example. All of them. What are they? Okay, I didn't find. But then I looked in the physics literature, and then I've seen formulas. For these guys, which are wrong. So be careful. If you are ever interested in translation invariant star products, and if you look in the physics literature, you will find wrong formulas. But it's not because they are wrong that they are not interesting. So they are very interesting formulas, in fact. But they don't give the whole space of translation invariant star products, but almost, but not all of it. So we thought about that a little bit with Louis 2 or 3 weeks ago. Okay, and then we arrived to the following conclusion, which is that if you have a star product or a formal two-code cycle on this group, on the vector space, on a symplectic vector space, okay, then the distributional kernel of any translation invariant star product is the following. It has this structure here. So it depends on the distribution. Okay, so the space of invariant star products is actually parameterized by a space of convolution invertible formal distributions on V. Okay, so you have you take such a distribution, okay, and you suppose that it's invertible as a convolution operator. Suppose that you therefore have another distribution which has a kernel that you call V. Okay, and you define those two very simple things. So first, you define the multiplication operator of a function by a phase, okay. And then you consider a complex structure. And then what you have is the following: is that the translation invariant star product is here you find the Weyl phase, the Weyl kernel, okay? But then it's modified by a multiplication, okay, of some by some object, by some formal number, if you want, which is written like this. So, okay, you see here this this object here that I defined, okay, multiplication by a phase. Here you have something on the square of V of the vector space, okay, which is again something of the same type, okay. And then you see that you have the Weyl quantization of this 2-point distribution, and then you have an integral on an intermediate variable which I call y, which is there. And then, okay, whatever it is, but then I would like to make this remark to Philippe in particular, that you showed us this very nice star product. Okay, you used, okay, and in this star product in the expansion, you had this Pochhammer multiplication and quotient, right? You remember that. And here you see you find the same. You find the same thing, same structure. So you have this, what I would call Pochhammer thing that depends on two indices, x1 and x2. And then you have and this is at the numerator. Okay, u is the numerator and v is the denominator, because v is the inverse. Okay, distribution, convolution, distributional inverse. Okay, and then there you find the product of v and v, evaluated in this at this point, which is exactly this point. So y, it should be y minus x1. And so you see the structure. Pochhammer, let me remember what you wrote. Pochhammer, p plus q minus t, Pochhammer p minus t, Pochhammer q plus minus q plus t, something like that you had, more or less. I don't have the exact formula in mind, but this is very, very, very similar. Okay. See? Right, but you have this intermediate, that's the intermediate thing, right? You have, yeah, there is a really, you have this intermediate variable upstairs and downstairs. So this is really the same, this way, of course you agree. I mean, this is really the same type of things. Yeah, I still have 2 minutes, right? Okay. Okay, so this is the thing, and what you don't see in this formula, of course, you see it here. Okay, the Weyl formula works for in the Bahns-Schultz, but what you don't see in this formula is that actually all the PCs in our analysis with Louis on this Kohn-Nirenberg star product, all the PCs that you find in this additional factor that defines the general kernel for translation-invariant co-cycle, all these P's actually are adapted to the method that we used for the Kohn-Nirenberg star product. So as soon as the analysis is compatible, of course, I didn't say anything about the analysis at this level. I'm talking about formal star product, okay? But of course, now you see that, okay, certainly you can give a meaning to those things. For example, considering U and V of Olbermann type, and see what kind of things you can build up in such a way that this additional factor makes sense. Okay, so the thing is that if you write it down, then you see that all the pieces are there. So actually, you can pursue the same thing. Okay, so I'm pretty sure that we are going to get this type of theorems for quite large class of invariant product. And so now, let me just not say anything more.
Thank you very much for the talk. Are there any questions?
So I think then I can ask a question. Here, Pierre? In the audience?
In the audience, where are you? Hi, okay.
In the very beginning, you said that if you deform with the twist, the module category, you do not obtain a symmetry, but in the formal setting, this is true. You obtain a deformed symmetry also with the twist.
You obtain, no, I didn't say that. I said the point is that your symmetry is deformed.
Yeah, this is, okay, then I understood correctly. Is this also true in the non-formal setting, or you?
That's exactly the point. That's exactly the point of my motivation. So Perfect. You have these twists, which are available in the smooth category. One theory. You have another theory about quantum group in a topological context as well.
Sure.
But one theory is smooth, and the other theory is a C star. And there is no clear link between the two. So, for example, the twists that are here, if you try to construct using formal IDs that you have in the formal category, things that you are talking about, right?
Exactly.
If you try to do the same at the non-formal level with the twist, you produce objects that are quantum group-like, but that are not locally compact. So it doesn't work. And on the contrary, if you start with locally compact quantum group locally compact that are locally compact at the C star of a Neumann level, you have twists, very nice, okay? But they are, for example, of the type of Kohn-Nirenberg. So it doesn't work to get
Perfect.
Genuine universal deformation formulas in the smooth context. And I like very much this.
Yeah, it's very nice.
Any more questions? There.
So the Bahns-Schultz construction is with tempered distributions, obviously, and you were also at some point working with tempered distributions. And then on the last slide, we saw just plain distributions. The last slide that we saw. So obviously, if you go back some, so
this one?
Yes.
Yes.
So could you maybe amplify what role this difference plays, or whether you need to consider Schwarz distributions at some point, or really everything works with general distributions?
I think I didn't get your question.
So, I mean, here you just...
I have a translation-invariant star product here. And I know that all of them at the formal level are of this type. And then what is your question?
So you don't need to have tempered distribution.
At this level here, it's formal.
Okay. Yeah. Okay.
At this level, it's formal. And now you're completely right. You can certainly require, in particular, the Kohn-Nirenberg star product is of this type for some U, and this one is non-formal. So I guess there should be a way. Okay, I have no idea how, right? At the moment, we are thinking about that. We wrote this formula a few weeks ago, and then we went to the beach, basically, because it's a holiday period, right? So, but I'm pretty sure that there is a way to impose conditions on this guy in such a way that this factor would make sense. And I guess that the condition must be similar to the S prime gamma Hermander condition, okay? Because you see what appears here, you have this guy here, which is precisely the co-cycle associated to to the Weyl product, and which precisely has the property of preserving this space of temporal distribution on the square. So I guess that you would have, and that's a very good question, you would have indeed same type of Olbermann conditions on the distribution U, which produce your translation invariant star product. Yeah, but I don't know how. No idea. We should do.
Thank you.
Can I ask a question? Can you hear me?
Yeah, I can
yes.
hear you.
Hi. Yeah, thank you for the talk. I very much like your method of proof. So I think this is interesting, obviously. I also had a question in a similar direction of what I think Arne just asked. I think I recognize his voice. Which is on the slide where you consider all these translation invariant co-cycles. You say that these kernels are manageable by the methods you use, the method of proof. You're manageable using the same methods. But now you said you don't know yet how to implement analytic, I don't know, structure, some additional structure in order to have this expression make sense as an oscillatory integral, not just a formal kernel. I don't understand. So this manageable using the same methods. This is sort of the hope, and this is what you will be working on. I suppose.
Yes, you're completely right. I mean, this is totally ununderstandable because I'm talking about the formal setting, and then I'm talking about the same method, blah blah. So this is not, of course, not correct. But the thing is that if you look at this thing, right? If you look at that, then in fact you see that there are. I should enter in the details, and I don't want to do that at the moment, not here. But you will see that there are. It decomposes into pieces, right? It decomposes into pieces, and these pieces are precisely of the type you need to run the machinery we have run with Louis in that situation. So if you can resum, in a sense, if you can resum everything in such a way that, in other words, in such a way that this thing would make sense, okay, and the way you resum is by integration by part, as usual, okay? If you can resum that, then I'm pretty sure that it's gonna be working. That's the idea. I didn't do it, so I don't know.
I see. Thank you. Thanks.
Are there any more questions? Doesn't appear to be the case, so let's thank you again.